Welcome to Spring LIB.
Okay, so we're doing chapter 29, problem 25. So in this problem, we have a rod here, length L, and they call this side A, this side B, and it's moving in this direction at a speed V. So this is all in a magnetic field pointing into the page. The vector sign, okay. So it tells us that L is 30 centimeters. And it says the magnitude of B is 0.45 Tesla. And it's moving at 5 meters per second in the direction shown. So, part A asks, what is the potential difference between the ends of the rod? So, we know that a conductor moving in a magnetic field may have a potential difference induced across it depending on how it's moving. And we know that the induced EMF from the equations is given as speed times the magnitude of the B field times the length of the rod times the sine of this angle phi. Phi is the angle between the velocity vector and the magnetic field. So this is the angle between these two vectors. Okay, so now we can just calculate this, and we know that for this case, since V is in the plane of the screen here, and B field is into the page, we know that phi for our case is 90 degrees. So we're evaluating this, we have 5 meters per second for the speed times 0.3 meters for the length. 30 centimeters is 0.3 meters. And then times 0.45 Tesla. And then sine of 90 degrees is 1. So that is easy. We plug this in and we see that the induced EMF magnitude is 0.75 volts. Awesome. So for part B, we want to figure out which side has a higher potential. So an easy way to do this is by figuring out which way the charges will be pushed. So we know that the force that these from the magnetic field is given as QV cross B. So using the right hand rule, for a positive charge, V, you can just take V cross B. V cross B gives the right hand rule of pushing the positive charge this way. So that means the negative charges are pushed this way. So since positive charges are pushed to B, then B is the higher voltage. Easy enough. Because the voltage is always higher, or the higher potential, sorry, as a higher potential, I should say, instead, because the higher potential voltage is always at the place where the positive charges accumulate. Okay, let's go to C. So C asks, when the charges in the rod are in equilibrium, what are the magnitude and direction of the electric field within the rod? Okay, so the magnitude is just given as the voltage divided by the length. So this is easy, which is 0.75 volts over 0.3 meters. So we know the magnitude is 2.25 volts per meter. Awesome. So the direction of E is also easy because we already know that the positive charges are pushed to B and the negative charges to A, and E always points from positive to negative. So this points from B to A. Cool. So now D, that's where the positive charges accumulate. We already said positive charge at B. because of the force argument here. So that's good. Let's get a new page here. So for E, so if the, okay, so let's just draw the rod real fast. This is A, B, and V is this way. Okay, so for E it says, what is the potential difference across the rod if it moves parallel to AB? So that means in this direction or this direction, or if it moves out of the page, directly out of the page. So this is parallel, and II case was out of the page. Okay, so first let's talk about the parallel case. So the parallel case works the same way now, but since we're moving in this direction, our L becomes the width of the rod. And usually when we're talking about a rod, these widths have no appreciable thickness. These rods have no appreciable thickness, which means L then becomes 0 when we're going parallel. So that means there is no EMF. Okay, awesome. And now we can go to the second case, and if it's going directly out of the page, there we know that the magnetic force was given as QV cross B. But now, if this is out of the page, V is out of the page, and B is into the page, this is always 0. So no force, we can't have any EMF. Okay? Awesome.